Biomedical waste management is a critical field focused on the safe handling and disposal of hazardous biological materials. This presentation provides an in-depth exploration of specialized waste streams, specifically focusing on the complex protocols required for radioactive materials within healthcare environments. Understanding these protocols is essential for ensuring the safety of healthcare workers, patients, and the general public, while maintaining strict compliance with national and international safety standards for hazardous waste.
Radioactive waste management in medical settings represents a unique challenge within the broader scope of hospital waste. Unlike infectious or chemical waste, radioactive materials possess physical properties that require entirely different containment and disposal strategies. This section will detail the regulatory frameworks, physical principles of decay, and specific storage requirements that differentiate radioactive waste management from standard biomedical waste procedures used for sharps or pathological materials.
Separate regulatory authority is the foundational principle of radioactive waste oversight. In many regions, this waste is governed by specialized national atomic agencies, such as the Atomic Energy Regulatory Board, or AERB, in India. These bodies set the technical standards for handling isotopes. Because of the unique risks involved, radioactive waste management falls completely outside the jurisdiction of standard pollution control boards, which typically oversee general biomedical waste, requiring specialized licensing and reporting. The physics of decay dictates how we handle these materials, as radioactive isotopes cannot be neutralized via heat, steam, or chemicals. Traditional sterilization methods like autoclaving or incineration do nothing to stop radiation. Instead, their decay is an immutable atomic constant based on the specific isotope's half-life. This means the radioactivity will only decrease over a fixed period of time determined by the laws of physics, regardless of any external physical or chemical processing applied to the waste. The principle of delay and decay is a cornerstone of medical physics. It serves as the primary protocol for short-lived medical isotopes, such as technetium-99m, which is frequently used in diagnostic imaging. This management strategy involves securely storing the materials until natural atomic decay renders them harmless. By simply waiting for the passage of time in a controlled environment, the hazardous radiation levels drop naturally until the material can eventually be treated as non-radioactive waste. The 10 half-lives rule is the mathematical standard used to determine waste is safe. It dictates that waste must be stored for a duration equal to 10 half-lives of the isotope present. This specific time frame is chosen because it reduces the remaining radioactivity to a safe 0.1% of its initial potency. Once the material has reached this 1,000th level of its original activity, it is generally considered to no longer pose a significant radiological hazard to the environment or personnel. Lead shielding requirements are essential for the physical infrastructure of storage. Storage rooms must feature specific lead shielding, often calculated using half-value layers, which is the thickness of lead required to reduce radiation intensity by half. This structural precaution protects hospital staff from ambient, long-term ionizing radiation exposure. Without proper lead-lined walls and containers, the gamma rays emitted by stored waste could penetrate standard construction materials and pose a health risk to those working nearby. Dilute and disperse is a strategy used for very specific types of waste. Ultra-low-level liquid radioactive waste can be discharged into municipal sewage systems under very controlled conditions. This method works by relying on massive volumetric dilution, strictly within AERB limits. By mixing small amounts of low-activity liquid with vast quantities of water, the concentration of isotopes becomes negligible, ensuring that the final discharge does not exceed safety thresholds for the general environment. Concentrate and contain is the protocol used when isotopes do not decay quickly. Longer-lived isotopes require physical concentration and sealed containment to prevent any leakage into the environment. Because these materials remain hazardous for years or decades, they must be transferred to secure national atomic repositories. Unlike short-lived isotopes that stay on site, these materials are packaged in specialized casks and moved to long-term government-managed facilities designed for permanent geological storage. The Radiation Safety Officer, or RSO, is the central figure in institutional compliance. They are a legally mandated specialist required in any facility handling radioisotopes, ensuring that the hospital meets all national safety codes. The RSO is responsible for calculating decay formulas, monitoring ambient radiation levels with specialized equipment, and authorizing disposal. No radioactive waste can be cleared for release or transport without the direct oversight and signature of the RSO to verify its safety. Thank you for completing this lesson on radioactive waste management in medical settings. We have covered the regulatory requirements, the physics of half-lives, and the practical methods of shielding, storage, and disposal. Maintaining these rigorous standards is vital for the safety of healthcare professionals and the integrity of our environment. Please ensure you review your local institutional guidelines and national atomic energy regulations to remain fully compliant with these life-saving safety protocols.